Welcome to Zeiss Inspect Correlate. In this video, you'll learn how to perform a simple motion analysis. I'll show you how to visualize displacements with colored vectors indicating the direction and extent of the displacement, and how to check points of interest in more detail. If you want to try Zeiss Inspect Correlate, take a look at the description below. There, you'll find links to download the software, request a free trial, and download training data. To perform a motion analysis, you need a project in Zeiss Inspect Correlate that contains 2D or 3D images or video footage of your test. The testing object should feature reference point patterns. I'll use a project containing data that was acquired with an Aramis system. That's why I can simply open the existing project. As you can see, the testing object, a model of an excavator, features reference point patterns. Reference point patterns can be used to analyze displacements and rotations, including 6 degrees of freedom analysis, velocity, acceleration, distance, angles, and much more. Because we're working with 3D data, you can switch between the left and right camera image. Simply click this button in the 3D toolbar. But don't worry if you're working with 2D images. The workflow I'm going to show you in this video is the same for 2D and 3D data. Now let's get started with the motion analysis. We're going to analyze how the superstructure of this excavator is moving relative to the undercarriage during the digging process. And here's how to do that in Zeiss Inspect Correlate. The first thing you need is 2 point components. One for the superstructure and one for the undercarriage of the excavator. The point components allow the software to identify and track the reference points over all stages in the project, thus allowing the software to compute the motion analysis. To find out more about the working principle and computation, take a look at the Tech Guide article, Introduction to Digital Image Correlation and Strain Computation. To create the point components, click Define Component in the main toolbar and select Point Component. Now you can see that the software highlighted all the measured reference points in green. You can now add the points to the point component. Let's start with the superstructure. Name the point component up here. To add points, hold Ctrl and click the points you want to add, or use Ctrl and the left mouse button to draw a rectangle and select all points within the rectangle. Again, if you need help, look at the tooltip down here. A point component must contain at least 3 points, but we recommend a minimum of 5 points. Let's take a look at the function dialog. The component type for this point component is rigid. That means that the component itself is only deformed minimally. Therefore, the location of the reference points relative to each other remains the same throughout all stages. This default setting works well for most applications. If it doesn't work for you, you can change it to deforming or adjust the expert parameters. For more information, please have a look at the Tech Guide. In the table underneath, you see all the points you added to the component. The software assigns a unique ID to each point, which is identical in all stages. This allows the software to identify and track the points. Now, since we also need a point component for the undercarriage, click Create for this one. And repeat the process for the point component undercarriage. If the tooltip is in your way, you can move it. Name the point component, select the points, and then click Create and Close. When you look at the Explorer under the part, you'll see 2 new categories: nominal elements and actual elements. They each contain 2 point components: superstructure and undercarriage. When you create a point component, the software automatically creates 2 a nominal, and an actual point component. The nominal point component represents the original state of the component, so the state in the reference stage. It's only relevant for more complex measuring setups, for example, measuring with multiple cameras. If you want to find out more, check out this What's New webinar from 2022. The actual point component is identified over all stages and used to compute your analysis. Now, in case you made a mistake or want to change certain parameters, use the function Edit Creation Parameters. Simply select the element you want to edit, say this point component, right-click it and select Edit Creation Parameters, or simply press F4. Please note that you must edit the nominal point component if you want to add or delete points. If you want to change the component type, for example, edit the actual point component. The software automatically recalculates all the dependent elements, checks, and even report pages. Please note that the parametric inspection, which is the concept behind this functionality, is only available with a Pro license. Next, you need to create an alignment to transform the measuring data into a suitable coordinate system. Click Create Alignment and select 3, 2, 1. Please note that alignments should be created in a stage without deformation. So make sure you're in the reference stage, in this case the first stage in the project. Use Ctrl and the left mouse button to define 3 points for the Z-plane, 2 points for the line to define the Y-plane, and 1 point for X. The directions of the axes might look different for you. That depends on the order in which you click the points. Use the options Plane Positive and Line Positive to adjust that. Now the intersection point of the X, Y, and Z planes is the origin of the coordinate system. To display the coordinate system in the origin, use the keyboard shortcut F10. To hide it again, use F9. In addition to the alignment, we need an RBMC, short for Rigid Body Motion Compensation, for the motion analysis. Here's why. First of all, we need to compensate any sensor movement. When computing the results for the motion analysis, the software cannot differentiate between the sensor moving and the object moving in the image. In this short clip, you see that everything is moving. With an RBMC, we can compensate the movement of the sensor by fixing the table. Reason number 2 is you can analyze the motion of one component relative to another, which is what you see in this short clip. Here, we want to evaluate the movement of the fan relative to the fixture. In our project, we want to measure the motion of the superstructure relative to the undercarriage. So we'll compensate the movement of the fixture or the undercarriage with an RBMC. And lastly, you could also use an RBMC to analyze the deformation inside a single component. In this clip, that would be the movement of the fan in itself, say bending of the blades, for example, compared to the reference stage. Like alignments, you can find RBMCs in the main toolbar, and you can create multiple RBMCs in your project. Let's create an RBMC. Click Create Alignment in the main toolbar. Under Rigid Body Motion Compensation, click Transform by Component. Then select the component you want to use for the RBMC. In this case, that's the component undercarriage. You can find the RBMC in the Explorer, under Alignments, Rigid Body Motion Compensations, and also up here, next to the alignment. Here you can disable the RBMC or switch to a different one if you have multiple RBMCs in your project. Now that we have point components, an alignment, and an RBMC, we're ready to check the displacement of the superstructure against the undercarriage. Since we want to evaluate the point component superstructure, display it exclusively in the 3D view. Then click Inspect all visible actual elements in the main toolbar and apply the check Displacement. If you're only interested in how much the superstructure moves up and down, use the check Displacement Y. The result is a vector field for each displacement check, indicating the direction and extent of the displacement for all the points in the point component. This gives us a good overview of the component behavior over all stages. You can apply deviation labels to the vector field to obtain discrete values. To do that, open Point Inspection's Deviation Labels. You can adjust and scale the legend by clicking the upper or lower limit and linking them to scale the legend symmetrically. You can also adjust the scaling so that it either represents the values of the current stage or the values over all visible stages. To do that, right-click the legend and under Scaling, select the option you want. You can find all the vector fields in the Explorer under Inspection, Surface Comparisons. So much for evaluating the entire point component. Next, let's look at a single point of interest. The benefit here is that we can get more detailed information about the point behavior over all stages, all in a single label. To create the point, click Point Inspections in the main toolbar and select Point Inspection. Press and hold Ctrl and click a point on the point component. You can find the point in the Explorer under Actual Elements, Geometries, Point. Hide the point component superstructure, then click Inspect all visible actual elements in the main toolbar. Hold Ctrl and select all 4 checks here. As you can see, all 4 checks are displayed in a single label. To document the result of this motion analysis, let's create a report page. Simply click Create Report Page in the main toolbar, and instead of Image, select Video here to create a report page with a video showing the displacement over all stages. You can also adjust the duration of the video here. That's it for the simple motion analysis. In case you haven't watched it yet and want to find out how to perform a simple strain analysis, have a look at the video Perform a Simple Strain Analysis in Zeiss Inspect Correlate. If you're curious about reporting, check out the video Reporting with Zeiss Inspect Correlate. And if you're looking for a more comprehensive training, check out the Inspect Correlate Aramis Basic e-learning. You'll find the link in the description below.